Here's the idea. I went to Home Depot recently, and I noticed something I didn't notice a year ago, which is that you can now go to Home Depot, and if you go in the sort of lighting aisle, I'm sure this is true of other stores, big box do-it-yourself stores as well. If you go into the lighting aisle, there's now a whole range of different LED lights you can buy that are pretty reasonably priced. So you can go buy LED replacements for incandescent bulbs in a lot of applications now. And the price of LEDs is dropping dramatically over time, and really quite rapidly. The bulb itself is still expensive relative to the cost of an incandescent bulb, but what's great, there's a couple great things about LEDs. One is that they last much longer than incandescent. There's no filament to burn out. It's a solid-state technology. The other thing which is great is the energy costs for producing the same amount of light for an LED are a small fraction of what it is for an incandescent bulb. So in particular, I'm referring to, this idea for this application came from a paper in the Journal of Physics D that was published last year. And this is some physicists who teamed up with an economist to write this paper. They estimate that that soon it will be the case that they do two things. First of all, they estimate the cost of using a 75-watt bulb for an hour, or actually 1,000 of those things. So that gives us a measure of illumination called megalumen hours. So the cost of 1 megalumen hour is $9. So that's sort of the current cost. The equivalent amount of illumination provided using LEDs would have a much smaller cost of 44 cents. So roughly 5% of the current cost. Okay, so that's great. We're thinking about something which we demand, light, and there's this fairly near-term prospect of a dramatic decrease in the price of that service, if you like, or that good if you prefer. Okay, so we got a 20-fold decrease in price of light. And the question I'd like to think about is, what does that mean? What does that mean for consumers? What does that mean for society? What does that mean for energy demand? Those are the questions we want to answer. All right, so this is sort of the first step we want to do here. So this is drawn from the same paper, which is to think about, I want to think about the commodity space for light, and then I want to think about preferences for light. So maybe I should say it before I turn to the diagram, actually. So first of all, what's the appropriate commodity space, do you suppose? Thinking about demand for light, like one of the goods, better be light. We'll measure it in megalumen hours or something. So let's think of a commodity space that involves that. And I'm going to call this light, and I think we'll measure it in lumen hours. What's the other good? What's the other element of the commodity space? Yeah, let's go. Let's just, for this classroom purposes, actually, works to get you published in this journal too. We'll just say that everything else is other goods. So food, clothing, automobiles, all the other goods we can think of, we'll just lump into a Higgsing composite and call it other goods. Okay, so that's a reasonable version of the commodity space. Now here's some work they did on historical demand for light. So let me tell you, I have to explain some of this stuff. So the stuff on the vertical axis here is actually petalumen hours per year is a measure of light consumption. This is for the entire. This is not for consumers. This is for the entire planet. Okay, so this is all the people on the planet. So this is a double log scale. So anyway, so we have light consumption on the vertical axis here, and on the horizontal axis, what they have is GDP is here multiplied by the cost per lumen. Divided by the cost of lumen multiplied times the parameter beta, and they estimate beta to be a quantity 0.0072, and it doesn't take too much imagination to see that that'll be like the slope of this line. If you didn't have beta, it's the slope of this line. So what we've got here broadly is light demanded on the vertical axis, and something to do with income on the horizontal axis. So what kind of graph should you be thinking of here? It's demand for light versus income. It's an angle curve. This is basically an angle curve for light. And this diagonal line on this double log graph has a slope of 1, but we've got beta here. And what they find here, the points here are different countries in different years. So it's kind of cool. So they have some very old data for the UK when people were still using whale oil as the main source of illumination. So back in the 1700s, and then candles around there someplace too. So UK before 1900. And what you can see is that as GDP increases, light demand increases, light expenditures increase in a more or less linear way with this thing. Then when we got into more recent data, we got not just the UK, but we got other countries too. So we have the US up here. We have OECD countries here. We have the former Soviet Union, all these sort of gray dots. I guess this is Australia, New Zealand put together. The point here is that all these things fall more or less on this 45-degree line. Maybe I'm tempted to ask this, maybe I'll say this. This graph is constructed so that if these points all lie on the 45-degree line, then it means that there's a unitary income elasticity for light. So the historical data they're providing suggests something close to unit income elasticity for light demand. Now we know what do we know about what utility function do we know that has a unitary income elasticity of demand for different goods? The same Cobb-Douglas or logarithmic one we've been using all along. So if we have this, actually I'll write it in this form. Let's call it light. Let's call the other good Z. What we can do is write this as log of light plus 1 minus beta log Z. Okay, so let me say two things. First of all, you know, because we worked it out, that this thing has a unitary income elasticity. It's also true that if we have a demand system where all the goods have unitary income elasticities, there's always a representation of preferences that looks like this. So we can use these preferences. If you buy the claim here, these authors are advancing, that in fact income elasticities are unitary, that means we can use these preferences to model the demand system. So that's kind of cool. All right, so this is the demand system. I'm going to use this graph here to justify using a set of preferences just like the ones we've been working with. Isn't that convenient? Now let's go ahead and think about how this change in price, this drop in price from $9 to 44 cents, will change the demand for illumination. Okay, so this just says what I said a moment ago. Since expenditure shares or income elasticities here seem to be kind of constant, so beta is the expenditure share for light, by the way. This is kind of interesting too. So this is an estimate based off the GDP figures. It says that 0.72 of 1% of world income is spent on illumination. Okay. Anyway, so that seems not to vary across time or place very much if we buy the data in this graph. If that's the case, we can use this kind of utility function. I already said that. And yeah, that's what I said. Here we go. Okay, so now here's a question I want to try to answer on the board. Here's an estimate of global income for 2010. The estimate of global income, global GDP, if you prefer, is $60 trillion. That's in 2010 dollars. Okay, so if we have in income, Y, for the globe. So this is where we're going to be interested in global demand for lighting in 2010. How could we work out what that is, knowing prices and income? We've got this beta. We've got a Marshallian demand for light. It tells us that light should be equal to beta times Y divided by the price of light. Let's do that this way. So that's exactly right. So global demand in 2010 should be equal to $60 trillion times beta, which is 0.0072, all divided by the price of light. And I want to use the same units. I want to use the same units of prices, which was, sorry, I just had this on the first slide. Well, we'll measure it in megalumen hours, so it's $9. Oh, sorry. So I want to do before and after. Sorry. So global demand, yeah. So global demand at current prices, and then we're going to imagine we substitute with LEDs. Okay. So somebody with a calculator, tell me the answer to this, please. So the units here should be megalumen hours, I guess. So it should be 0.0072 times 60 trillion divided by 9. Just give it to me in scientific notation. It's going to be a lot of zeros. Trillion is 10 to the 12th. Yeah. Just do the scientific notation. 1.8 times 10 to the 10th? Is that what you said, 10 to the 10th? 4.8, pardon me. 10 to the 10th. Okay. So, and this is, again, expressed in megalumen hours. So it's, I guess, hundreds of millions of megalumen hours if you want to work that out. Okay, so that's current demand. Now, what if we change? So let's keep income fixed, but imagine that everyone's got LEDs now. So with LEDs, we'll have global demand equal to the same expression. Namely, we'll have beta times Y, equal to 60 trillion, but divided now by 0.44 instead of by 9. And so what's that equal to? $9.8 times 10 to the 11th. Okay, so this is the claim about what demand will be if we introduce LEDs. Okay, so what we see here, it shouldn't be surprising. We see a big drop, a proposed big drop in the cost of lighting. We see a big increase in demand for lighting. Now, let's take just a moment and sort of square that with our individual consumer experience. If you had LEDs, the cost of lighting stuff fell a lot, how would you respond, personally? So if we magically waved our economist wand and turned all the incandescent bulbs in the world into LEDs, what would you do differently? Yeah, I spend a lot of time turning off lights in my house right now. I have small children who always leave them on. So I spend time turning them off and scolding my children for leaving them on. So I would do that less. What else? We're getting, so this is an increase. This is an increase in demand of 20 times, in fact. So if we see a decrease in price, how might we see this manifested in terms of a great increase in demand for light? Or would we? I mean, we would say no, we've already got enough light. Yeah. So the guys who wrote this article, I mean, it was point out that, wrong way. Let me show you this picture again. So our demand for, this is a log scale. So demand for light has increased hugely between, over the last century. In the UK, for example, the population of the UK hasn't increased that dramatically over the last 100 years. What's different is that people do use more light in their homes for sure, but a really big difference is that there's a lot of outdoor lighting. Street lights weren't common except in very major cities, major streets in 1900 in the UK, and they are now. If you look at sort of satellite pictures of our planet now, you can get a good sense of what parts are highly developed or have high-income households by seeing how bright it is. So the speculation these guys engage in, I think it's plausible, is with a 20-fold decrease in the cost of light, we'll light our homes more of the time. We'll also light much larger expanses of outdoors. Yes. Yeah. That's right. So kerosene is still an important source of light for a bunch of viewpoints down here, right? And for some of the developing countries, I guess aren't going to show up here so much. But there's been a variety of technologies that show up here. So whale oil, kerosene, candles, those all those technologies have changed as people demand more light. And as they change, the cost of getting light, as you point out, the cost of getting light from kerosene is quite high compared to getting it from coal-fired electricity generating plant, for example. And as those costs have fallen, we've demanded more light. And so there's a question about whether we'll continue to do that. If we get a 20-fold decrease in light, then we'll consume 20 times more light. These guys sort of argue well, but we don't really know. Yeah. Yes, it's a sort of strong claim about the rebound effect. In fact, that if it's so I don't want to define the rebound effect right now. The claim is that the claim being made here is that all the past decreases in cost of light have been reflected in a proportional increase in light demand. So it's all rebound in that story. And you can see that projection here. This is, in 2030, they think it's going to be replacement of a bunch of stuff with LEDs, and so this one's still going to lie on the same line. Now, the consequence of this, and this rebound question brings us to this, I think I won't go through this carefully, but if it's the case that we just increase our light demand proportionally to the fall in price, what are the consequences for energy demand? People talk about using LEDs to reduce energy demand. What would we actually expect to happen if people behave this way? And we'll assume for the moment that energy prices remain constant, which is, I'm sure not true, but suppose it is for the moment. So, yeah, so Wes has the answer. This says no, we shouldn't see any impact on energy demand. All the change in price is going to be translated into greater demand for light, and the total amount of demand for energy will remain constant. It's not going to be affected by this new technology, by this new energy efficient technology. The efficiency will all be translated into more light, not less energy use. Yeah. Well, so the question is, why wouldn't you use the savings to buy this stuff? Everyone's doing that. It's not like you're taking all the savings from this. The story here is you have a fixed expenditure share. So you keep expenditures on light fixed as a share of your total budget. If light prices drop a lot, that'll translate here into an increased demand for light. It won't affect other stuff in your portfolio according to this story. Okay, so let me stop there. I'll see you Tuesday.